If you look at the global scale, the projection over the same time frame is that energy use will increase by 40%. Pretty extraordinary, and in fact, coal makes gains on a global basis. And where do those gains come from? The blue line, North America, we're relatively flat. All the action is in China and India. 85% of the growth in world coal consumption is going to come from those countries. So if you're going to change something, I think it's useful to assess what your point of departure is. Where do we sit today? And there are roughly 540 coal plants in the U.S. Their net output is 337 gigawatts, and they provide a little bit less than 50% of U.S. electricity. Now, it is coming from an asset base where a good portion of it, about 15%, is greater than 50 years old. Then you've got another 20% roughly that's between 40 and 50 years old. So clearly those plants, while many of them have been upgraded over the years, they are candidates for retirement as we go forward. It's also the case that the coal fleet is far, far cleaner than it was a few decades ago. A very large fraction of the fleet has cooling towers that may need to be retrofitted to be consistent with emerging EPA regulations, and probably half of the fleet has ash handling systems that may ultimately need to be upgraded. So there's been a lot of progress, but there's still a lot of work to do. I think it really gives you a sense of the regulatory freight train that's coming down the tracks at the coal industry. Regulating water that goes into your plant, regulating water that goes out of your plant, further regulation of hazardous air pollutants, further regulation of mercury, tightening of particulate controls, particularly for the eastern states, tighter NOx and SOx controls. And so it really is a daunting amount of complexity that the average coal-fired utility in the U.S. faces. And there will be extraordinary amounts of staff power and money, capital, requirements for skilled labor to navigate through this process and ultimately implement the kind of environmental change that the policy community is looking for. And it won't be pretty. It'll probably be resolved in part by lawsuits, congressional intervention. But in the end, I'm very optimistic that we'll get it worked out. And over the next couple decades, you may lose 5 to 20% of the existing fleet. We will struggle through that because just because there are new regulations that say you need to do something, that doesn't mean $50 to $100 billion in capital instantly materializes for utilities to make those changes. It doesn't mean that public utility commissions will instantly allow you to pass those costs along to ratepayers. And so there will be some significant challenges there, and there is some potential for at least an interim train wreck. But as I say, in the long term, I'm optimistic. I think we end up with a slightly smaller U.S. coal fleet, but it's a cleaner fleet. It does come at a significant cost. Depending upon whose estimates you believe, it's probably $50 billion, $100 billion, maybe more. And should that debate carry us, as it has in the past, to calls for significant reductions, 30, 60, even 90% of reductions in carbon, that fundamentally requires an entirely new generation of technology that is so enormous in scale it pales compared to these shorter regulatory challenges, even though they are not insignificant in and of themselves. And so I think a place for innovators within industry, within government, and that's partly what we're trying to do in our effort at FutureGen to invest, is if for a moment we can dream beyond all those near-term regulations that are coming at us like a freight train, and try to identify what is the technology, or more likely technologies, that can help us leapfrog right past those. Wipe away, in large measure, all the emission concerns, substantially reduce the carbon associated with these plants, and do it at a cost that is affordable. It may not be affordable today on the initial plants, but as energy prices rise and the marketplace sorts itself out, I think we're quite confident that they can be competitive in the decades to come. So if there were 3 places in particular where I'd like to see a significant surge, and there is currently substantial progress in terms of new technology, it would be around near-zero emission systems, sort of 3 classes. And most of you are probably familiar with IGCC. Probably our best hope in the short run to get a commercial plant on the ground with 65% capture would be Southern Company's Kemper County plant. I'd also certainly like to see us strive as a nation to get on a plant on the ground that's an IGCC with 90% capture. Perhaps our best candidate there is the Hydrogen Energy California project at the moment. Both of those efforts capture their CO2 and send it off to enhanced oil recovery. That is a very valuable, albeit niche market. The second class of technology is oxycombustion. That's what we're working on in FutureGen with Ameren, with B&W, with Air Liquide, and about a dozen of our industrial partners. In this particular application, instead of burning coal with air and getting a very dilute CO2 stream in your flue gas, you burn it in the presence of oxygen and a recycled CO2 stream. You get a very pure CO2 stream on the back end of the plant. In fact, 97% pure. It's far more cost-effective to capture on the back end as a result of that high purity level. All the CO2 from the entire plant is captured at more than 90%, and it goes to these deep saline formations that I just talked about. The other class of technology, which is of course extremely important because we do have an existing asset base on the ground, is post-combustion capture. Probably the best early success we have there is AEP's 20 megawatt slipstream Alstom ammonia-based scrubbing facility they have in the back of their Mountaineer plant. It's one of their flagship facilities, and so even old school utilities can be pretty innovative when they put their mind to it. It captures at 85% carbon, and it's injecting that stream in the ground in a saline formation today, albeit at a smaller scale, and they have aspirations to bring that up to a commercial scale.
What we think is a truly game-changing technology, and something that normally people wouldn't think about as entrepreneurial nuclear power. Small modular reactors didn't exist a few years ago, or even the concept didn't even exist a few years ago. And a lot has gone into the concept for NuScale and others over the past couple of years. And we believe that there's a lot of merit in moving this forward and seeing what we can do to rethink nuclear power. Some of the components in there, a little different than what you'd see in a conventional nuclear power plant. And this is truly modular. This would be built in a factory and shipped to the site without fuel and fueled at the site. That's about 30% of the cost of a nuclear power plant is this nuclear steam supply system, and it would all be done in a factory base. And that creates a lot of economies of what we call economies of small, which kind of flies in the face of traditional nuclear, which most people think of. You need to have the scale to make it economic. We believe that you can also do it in a small way and in a smart way and also make it economic. It's not a radical design that's going to require a paradigm shift in how we're going to license this reactor. It's very much in the sweet spot of what the Nuclear Regulatory Commission has been looking for or looking at for years now. That core heats water, it rises through natural circulation. There's a helical coil steam generator in the middle, which is integral to the system. And the steam is created in a helical coil steam generator, and the water falls back down through natural circulation back into the core and heats up again. One other big item to take a look at here is the containment. So a traditional nuclear power plant, when you build a nuclear structure, it's what we refer to as stick-built. You build it on site, and most people when they associate looking at a nuclear power plant, they look at big containment buildings. This plant will not need a big containment building because the containment is actually integral as part of the module. So that big containment building that you see in a nuclear power plant of today is being replaced by this module that's 65 feet in height and 15 feet in diameter. It's also very good for seismic capabilities. It's actually, that module is within water, and it is on a trunnion that allows it to move so that if there's an earthquake, it moves with the earthquake. You can go from 45 megawatts to any multiple of 45 megawatts you want and build it in increments. And when you have a plant that, with this plant design that I'm showing you here, is a 12-module plant, 540 megawatts, you run a lot less risk of things like single shaft risk. So when one module goes down, you only lose one module. You only lose 45 megawatts versus the large shaft plants of today that are greater than 1,000 megawatts in the nuclear power world. When you have a problem, you lose 1,000 megawatts off of the grid. You can see the modules that are stacked up there on the left, they're all underwater, and this is all done below grade. So it's good for seismic, it's good for protection against anti-terrorism, and there's a crane that you see in there which is able to move those modules into a refueling station, and the efficiency of being able to refuel them every couple of months, one module at a time by taking one module off, adds a lot to keeping the costs of the operationally plant down. For a 540 megawatt NuScale plant, we're estimating that the capital cost, the EPC cost, is in the range of $2.2 to $2.5 billion, which is $4,200 a kW. Marginally less expensive than on a dollar per kW basis than a large plant, but at $2.2 to $2.5 billion, you're not taking the huge risks of putting in a $10 billion facility. We have a test facility. We don't plan on having a prototype type plant. We have a test facility that's been in operation for about a decade at Oregon State University. That should reduce our regulatory risk as we go forward and prove out the concepts of our design as it's already doing. To get this done, we need to have some strategic partnerships. NuScale is a completely entrepreneurial type company. Right now we're venture capital backed. All private money has gone into NuScale up to this point. We'd like to get some Department of Energy funding going forward, but up to this point this has been taken on completely on the backs of private investors. As far as first 5 customers for NuScale, I'd say that the likely characters to begin with are in the U.S. We've taken a strategy of let's get our design through the Nuclear Regulatory Commission and then try to bring that around the world internationally, because the Nuclear Regulatory Commission certification is kind of seen as the gold standard around the world for a nuclear design. So it's likely our first customer in the U.S. will be a nuclear utility that already has a nuclear program, of which we're talking to a number of them, and we have a number on our customer advisory board.